Back Physical Science 20. This is the PW1.4 section. So we've looked at waves in general. We looked at one-dimensional, such as on a slinky or rope, two-dimensional, dealing with water, a little bit of three-dimensional, looking at sound. Now we look at light waves, properties and speed. So we looked at properties and speed of the other types. Let's look at light. So develop the ray model of light, explain what is meant by the meaning of luminous source, illuminated source, opaque, transparent, and translucent, and then solve problems involving the speed of light. One of the things that you ever discovered about light, although you may not have been conscious of your discovery, is that it travels in straight lines. When a narrow beam of light, such as that of a flashlight or sunlight streaming through a small window, is made visible by dust particles in the air, you see the path of light as being a straight line. When your body blocks sunlight, you see your shadow. Also, that indicates that light travels in straight lines. Also, whenever you locate an object with your eyes and walk toward it, you most likely walk a straight path. These things are possible only because light travels in straight lines. Based on this knowledge of how light travels, models have been developed that describe how light works. So we look at the ray model of light. Isaac Newton believed that light was a stream of fast-moving, unimaginably tiny particles, which he called corpuscles. However, this model cannot explain all of the properties of light. Experiments showed that light also behaves like a wave. In the ray model of light, light is represented as a ray that travels in a straight path, as seen in this figure here. The direction of which can be changed by placing an obstruction in the path. The ray model of light was introduced as a way to study how light travels and how it interacts with matter, regardless of whether it's a particle or a wave. Because as we'll see here, light can be thought of as a particle or a wave, depending upon the circumstance. Study of light is called ray optics or geometric optics. So first of all, let's look at sources of light. Rays of light come from sources of light. Our major source, of course, is the sun. Other natural sources include flames, sparks, and even fireflies. In the past 100 years, humans have been able to produce several other kinds of light sources: incandescent bulbs, fluorescent lamps, TV screens, lasers, and LEDs, light-emitting diodes, are each the result of humans using electricity to produce light. What is the difference between sunlight and moonlight? Sunlight, of course, is much, much brighter. There are also another important difference between the two. The sun is referred to as a luminous source. It emits its own light. In contrast, the moon is an illuminated source in that it becomes visible as a result of reflecting light off of it. So like in this picture, I think yours looks better than mine. So we can see the luminous source here, sun making its own light, projecting it to Earth. Whereas we see the moon because the sunlight reflects off of it. So we could be over here, it's nighttime, but the sun is reflecting off the moon. We don't see the sun, but we do see that reflection of the moon. And of course, if the moon is on this side, we'd have an eclipse. We would not be able to see that moon. An incandescent lamp, such as a common light bulb, is luminous because electrical energy heats a thin wire in the bulb and causes it to glow. An incandescent source emits its light as a result of its high temperature. A bicycle reflector, on the other hand, works as an illuminated source because it has been lit up by car headlights and it reflects in such a way that we see it. Illuminated sources are visible to you because light is reflecting off or transmitting through the object to your eyes. Media such as a brick that do not transmit light but reflect light are opaque material. You can't see through them. Media that transmit some light, such as air and glass, are transparent media. Media that transmit light but do not permit objects to be seen clearly are translucent. So you have on one end of the spectrum opaque. They do not allow light to pass through. You have transparent materials such as windows, which allow most of the light to transfer through. And then you have kind of in between, like wax paper, for example. It's somewhat transmits light, or a bathroom window that you can't completely see through. It's translucent. Lamps, shades, and frosted light bulbs are example of materials that are translucent. All three types of media you can see below. So with that, we'll look at the speed of light. For light to travel from a source to an illuminated object to be illuminated, it must travel across some distance. And of course, we looked at this. The speed is determined by distance over time, or displacement over time. According to classical mechanics, if you can measure the distance and the time, then you can calculate speed. For the 17th century, most people believed that light traveled instantly because it is so fast. Think about turning on a light switch and trying to measure how long it takes light to come on. Well, it seems like it's almost instantaneous, so that's what it was thought to be for a long time. Galileo was the first to hypothesize that light must have a finite speed, so it must have a speed limit, and to suggest a method of measuring its speed using distance and time. And kind of the experiment that he did was he stood on a mountain, and then he had a trusty assistant stand on another one, tried to flash light and time, and I think there was a mirror over here, and timed how long it took to come back. And of course it was way too fast to measure. So he wasn't able to do it. Danish astronomer Ole Romer was the first to determine that light does have a speed. Between 1668 and 1674, Romer made 70 measurements of the 1.8 day orbital period of Io, one of Jupiter's moons. So here's the sun, here's Earth going around the sun, here's Jupiter, and we have Io that's going around Jupiter. He recorded the times when Io emerged from Jupiter's shadow, so right here, so coming out of the shadow, and then noting it with a telescope. Oh, there it is. As shown in the figure, he made his measurements as part of a project to improve maps by collecting the longitude of locations on Earth. This is an early example of technology driving science advances. After making many measurements, Romer was able to predict when the next eclipse would occur. He compared his predictions with the actual measured times and found that Io's orbit increased an average of about 13 seconds per orbit when Earth was moving away. So over here, you could think of it as, oh, Io's gonna come out right now at a specific time. And then 6 months down the road, being able to see it, oh, it happened a little bit later. And of course, the reason why it happened later, because it took an extra bit of time to go this extra distance. So the light from Io reaching Earth here versus the light from Io reaching Earth when Earth is on the opposite side of the sun, there's an extra distance that light has to travel to reach your eyes. So yes, that proved that, guess what, there is a speed limit to light, because it takes longer for this eclipse to occur when the Earth is over here than when it is over here. So about 13 seconds more. So Romer believed that Jupiter's moons were just as regular as Earth orbits as Earth's moon. Thus, he wondered what might cause this discrepancy in the measurement of Io's orbit. So measurement of the speed of light, Romer concluded that as Earth moved away from Jupiter, the light from the new appearance of Io took longer because of the increased distance to Earth on the opposite side of the sun. Likewise, as Earth approached Jupiter, Io's orbit decreased. So going this way, oh, it happened sooner and sooner and sooner. So again, that extra piece there, that extra part, it took a little bit longer. So it took a little more time to travel from position 1 to position 3. As shown in the above diagram, there are 103 eclipses. Thus, for light to travel that diameter of Earth's orbit, it calculated that it takes an extra 22 minutes. Using the presently known value of the diameter of Earth's orbit, Romer's value 22 minutes gives a value for the speed of light to be 2.2 times 10 to the 8 meters per second. And today we think of the speed of light as being closer to 3.0 times 10 to the 8 meters per second. Thus, light takes 16.5 minutes, not 22 minutes, to cross Earth's orbit. Nevertheless, Romer was very successful at proving that light moves at a speed limit and not having a too bad a value figuring that out. Although many measurements of the speed of light have been made, the most notable were performed by American physicist Albert Michelson between 1880 and the 1920s. He developed an Earth-based technique to measure the speed of light. In 1926, Michelson measured the time required for a light to make a round trip between two California mountains, 35 kilometers apart. Michelson used a set of rotating mirrors to measure the time intervals. So it looked something like this. There is a rotating mechanism, an octagon, that had mirrors on it. And so light would be projected on this mirror, go out to a mirror that was 35 kilometers away, because you need a large distance to measure this very short time interval. And then over here there's a detector. So this thing was rotating, and the frequency was known of rotation, so that could give us a time to go 35 kilometers, come back 35 kilometers, and of course it hits a different face by the time it comes back, because it's rotating, and we can get a time measurement there. And the speed of light was measured to be 2.99 times 10 to the 8 meters per second, etc. For this work, he became the first American to receive a Nobel Prize in Science. Speed of light in a vacuum, so a space in which all the air molecules are gone and everything, is a very important universal value. Thus, it has its own symbol known as little c. And it is the little c that's in E equals mc squared. Based on the wave nature of light, the International Committee on Weights and Measures has measured and defined the speed of light in a vacuum to be 299,792,458 meters per second. For many calculations, the value of 3.0 times 10 to the 8 meters per second is precise enough. At this speed, light travels this far in a year, and that is referred to as a light year. So a light year isn't actually a measurement of time, it's a measurement of distance. So using that and figuring out how, using a time factor of 1 year, converting it into seconds, light travels this far. 9.46 times 10 to the 12 kilometers, which is 9.46 times 10 to the 15 meters. All right, we'll stop the video there and we'll do the example, and then we'll be done.